Okie dokie, today we are talking about reflection, specifically reflection in a plane mirror. So we have a few different learning goals today. The first is to be able to describe the law of reflection. The next is to know the different types of reflection. There are two. To be able to draw the image in a plane mirror, and to be able to describe the characteristics of that image made from a plane mirror. Now, whenever light is coming in towards a plane mirror, so right here is our mirror, light will come in at some angle. It doesn't really matter what the angle is, and it will bounce off the mirror because the mirror is a reflective surface. And so you're going to notice a few symbols here. The first is N. N stands for the normal. The normal is basically a imaginary perpendicular line to the mirror. You also have theta I, which indicates the angle of incidence, and theta R, which indicates the angle of reflection. So this blue line here represents our incoming light. We call that our incident ray. And in the red, we call it our reflected ray. So these right here are some important terminology you're going to need to know. Incident ray, which is this line, reflected ray, which is this line, angle of incidence, which is this theta, and angle of reflection, which is this theta. Notice the angle of incidence and angle of reflection are with respect to the normal, not the mirror. Common mistake. Now, the law of reflection basically says that the angle of incidence is going to equal the angle of reflection. What that means is this angle between the incident ray and the normal is going to be the exact same as this angle between the reflected ray and the normal. Through this knowledge, we can predict where a ray of light is going to be reflected. Now, there are two different types of reflection. We have regular reflection, or another way of saying that is specular reflection. This reflection occurs with a smooth surface. So in this picture, we have glassy, smooth lake water, and the reflection is precisely reflected. You can see the mountain up here, and it's reflected in the water. So that's specular reflection. You should notice that the incident rays in blue are all parallel to one another, and the reflected rays are similarly parallel because they're all maintaining that same sort of incident angle, reflected angle. Here's the other type of reflection. It's called diffuse reflection. Basically, diffuse reflection is what you get with a rough surface. This means that the reflected ray appears as if it will be all over the place. Now, the reality is it is still following the law of reflection. It's just a bumpy surface, and so it's not going to appear as if it's all lined up and parallel as it did with that specular reflection. Let's take a look at these individual incoming light rays. So here is our incident ray, and our normal is perpendicular to that surface, and we have our reflected ray. But if you compare that to over here, we have our incident ray, but because that surface, the parallel sort of line is coming out this way, that's where the normal is going, and therefore the reflected ray is a much wider angle. So each time the law of reflection is still maintained, it just looks a little bit different. So when we're talking about optics, there's something called an image that forms. The image is sort of the reflected object that we appear to see. This image is formed as a direct result of light bouncing off the object into the mirror and into our eyeballs. So what we have here is our object. In this case, it's a little yellow dot. It could literally be anything. Here it's a little yellow dot. And so light rays from the object move towards the mirror. So somehow they are bouncing off this object towards the mirror. And so these are all incident rays. And there could be any number of incident rays when considering the reflection off of an object. Then what happens is, well, it's a mirror, so of course those original incident rays are all going to be reflected off the mirror following that law of reflection. Notice, if I were to draw a normal down each line, you would notice that the angle of incidence is equal to the angle of reflection. Now, here's where it gets a bit tricky. When we're talking about the image, we can extend the rays of those reflected lines behind the mirror. So now we're sort of in an imaginary universe. And where those lines intersect is where the image appears to be. In this case, it's behind the mirror. Okay, so basically, the image is where the observer of the reflected rays thinks they are coming from. Now what I want you to do is pick up your phone, or a mirror ideally, and you're going to look into your phone screen or a mirror. A mirror is best really, but phone if it's what you have, and find an object in your phone. So you're looking for the reflection of an object in your phone. And if you stare straight at the object and sort of visualize where it would be on the other side of the mirror, then that's what it means by the image is where the observer thinks they were coming from. So, for example, if I'm looking into my phone and I'm looking at my glasses on the desktop, then it actually appears as if the glasses are sitting behind the phone, or in my case, the mirror. You'll have to try it on your own to understand. So, I mentioned earlier that these lines are called the extensions of the reflected rays, because remember, these are the reflected rays, and when we extend those lines beyond the mirror, they're called extensions of the reflected rays. So, an image forms when lines intersect. When the image is behind the mirror, it's known as a virtual image. By definition, a virtual image cannot be focused on a screen. And what that means is a literal screen, like a projector or a piece of paper. You cannot do it. If instead the image is formed by the intersection of actual light rays, it's called a real image. So far we have a virtual image and a real image. A real image can be focused on a screen. Here we have a curved mirror. Don't worry too much, we'll get into that next lesson. When we're describing the properties of the image, we use SALT, as in S-A-L-T, as an acronym to help us describe it. We have size, so is it smaller, larger, or the same size as the original object? So is the image smaller, larger, or the same size as the object? We have attitude, which basically just means is it upright or upside down? We have location, so where is the image relative to the other objects? We'll get into that more later with specific examples. And finally, type. We have already talked about real or virtual. Okay, so here is where we get into drawing a ray diagram for plane mirrors. Right here down the center we have my mirror, and here I have my made-up object. Now this object could be anything, but I'm not an amazing drawer, so we're going to use my happy little arrow. There are a number of steps that you need to follow to draw the image of an object for plane mirrors. So remember, over here we have our object, and we're going to create our image. Now, you'll come to realize that you should expect your image to be on this side for plane mirrors, and I'll show you why. Step 1, you're going to pick 2 points on your object. Minimum of 2 points. You should pick as many points as sort of like distinguishing features. In this case, distinguishing features are the top, bottom, and if you really wanted to be picky, you could pick the sort of ends of the arrows. Step 2, from those points, I'm going to draw incident rays. Now, the first incident ray I'm going to draw is going to be one that is perpendicular to the mirror, or perfectly parallel to sort of the ground. Now, if a line bounces straight into the mirror, the angle of incidence is 0. So that's an 8. Angle of incidence, so theta I, is 0, which means that theta r also has to equal 0. So my reflected ray is going to bounce straight back. And I've gone ahead and repeated that process with my second point of interest. Now, we don't have any intersecting lines yet. These lines don't actually count, so I have to draw another incident ray. Now, I can pick an incident ray going wherever I want to in the general direction of the mirror. It does not matter at which angle it meets the mirror, and the reason for that is when we're thinking about light bouncing off an object, we kind of consider there to be almost infinite amounts of light, and they're going to be bouncing in all different directions. If you can see it, you know that light is bouncing off the object. So I'm going to just draw this sort of arbitrary angle. Again, it doesn't matter what the steepness of my angle is. I could have drawn it over here if I wanted, over here, but I've kind of run out of mirror, so it's not great to do that. If I draw a normal, my reflected ray is going to be reflected, and each angle here and here will have the same angle. So the angle of incidence is going to equal the angle of reflection. Same thing up here. I'm going to draw that, and when I'm choosing where to draw my incident and reflected rays, I just try to keep it neat and tidy. So you see here I've kept them separate, and it just helps to keep better track of them. So you'll notice that I have all of my incident rays and all of my reflected rays. Incident rays are blue, reflected rays are red. But there is still no intersection of either incident or reflected rays. What this means is I now have to go and extend my reflected rays. Please note, you only ever extend your reflected rays. You do not ever extend your incident rays. So notice we now have an intersection. So this dot corresponds with this dot over here. And I'm going to do the same up here. And here's my other intersection, and so this dot corresponds with this dot. And now I'm able to draw my image. So I have found my image, and the only thing left for me to do for a ray diagram is to describe the characteristics of the image. You remember we use the acronym SALT. So S is size. Is it bigger, larger, or the same? In this case, it is the same size. A is attitude, where attitude means is it upright or inverted? In this case, it's upright. location, we have sort of with respect to other things going on. So in this case, is it behind or in front of the mirror? Over here would be in front, and this is behind. So we would say behind the mirror. And finally, type. Is it real or virtual? If you remember, I said that a virtual image was created by the intersection of reflected lines. The other way of remembering it is if it's on the other side of the mirror. I always think about it as, or I always used to remember it as, this is the real world. This is where the object actually exists. This is the fake world. The object doesn't actually exist on the other side of the mirror. And so that's the virtual image. And that just means we cannot project it on a screen. Now it's important to know that the image properties, or the SALT, for a plane mirror will always be the exact same. The size should always be the same, the attitude should always be upright, the location should be behind the mirror at the same distance, and the type should always be virtual. Notice the same distance. So in theory, we could take out a ruler and measure these distances instead of drawing our incident and reflected rays. Anyhow, that's it for drawing plane mirrors. I'm going to post another video for you to take a look at, but let me know if you have any questions, and good luck!